Hello, Matthew. You're in this room today, probably for this week or your holiday. By the way, you're on live. It doesn't mean you're on your show on the screen, but have you been?
Good. Thanks.
Enjoying your holiday?
Yeah.
What have you been doing?
Like, when my convention and stuff.
You what? Sorry. Okay, just waiting. There you go. Okay. Morning, Damien. Yeah, it must be 7 a.m. in Korea, so it's a bit dark. So people are joining from Korea now. Yeah, as I said, we are going through some relative velocity. We're going to revisit that, as that's not easy content to understand in just an hour or two. It needs quite a lot of practice. I also give you some situations that when we use the relative velocity. So let's start. When we're talking about relative velocity, okay, just need to turn it off. Probably the easiest way you're thinking about relative velocity is when you're riding on the bicycle, riding on when you're in the car. So I think when you come to here in this office, like you probably catch the train or you catch your mom dropped you off. Okay, so assume that you are in a car that is moving. Okay, now or like you're standing here looking up the cast that's moving in like 10 meters per second, let's say east to this direction here. Okay. Now, this is you, I want you like to put yourself into the situation. You are looking at the car that's moving to the east. Then, as you're not really moving, you can only measure the actual speed of the car that's moving in 10 meters per second to the east. Does it make sense? Okay. Now, what we have to consider here is you're on the ground. You're on the ground level. So you're at the ground, you're looking in the steady or stationary, the ground state, looking up the car that's moving in 10 meters per second to the east. So the velocity of the car is pretty easy. But what if you are inside the car? An important thing is you're not accelerating, which means you're moving in constant velocity. So assume that now you're the one in the car. Okay, well you're not able to drive now, so you're next to your mom or your dad. You're looking at the people who's on the ground. Okay, so this is me. I'm moving. When I'm looking you, so that's on the sitting down in there. I feel like I'm not the one actually moving forward. I feel like you're the one moving backwards in my perspective. If I just ignore about my movement, okay, I'll probably see that you guys move backwards. Similar things happen when you're in the train. Okay, when you see the outer view, you'll probably see that trees and outer people on the stations waiting for the trains moving backwards while you're moving forward. Does it kind of make sense about the relative velocity? I'm talking about not the actual velocity. I'm talking about your perspective, your relative velocity to your situations. So it depends on your situation here. You would measure the velocity quite differently here. So this is how we actually describe the velocity, show the velocity in them. when we say the velocity of the car, okay, that's a V stands for the velocity, C stands for the car, that's relative to the person on the ground. We write it as V, C, and G, just ignoring the excluding that relative here. This means the velocity of the car relative or measured by a person on the ground who's stationary, basically. Then it's pretty simple because you can imagine, you have to use imagination here. That yes, you're looking up the car to moving towards the 10 meters to the east. That means we just take that as, oh, that's a 10 meter per second to the east because car is moving towards the east. How do you mean? Okay, you get 10. I don't know. I think so. Oh, sorry. Okay. Maybe I shouldn't say that. All right. Okay. No, you didn't get 10. Ignore that. All right. We just started about revising the relative velocity because it seems like everyone's getting confused about the contents. Today, I'm going to give you some more situation questions related to. Did you bring your workbook by any chance? Okay, I'll give it pretty test. Okay, don't worry. It's okay. First day back from the holiday, everything's happened. All right. So start it again. When you assume that you're on the ground looking at the cars that are moving in 10 meters per second to the east, which means that you are actually looking at the actual car speed. But in terms of the relative velocity, we talk about in your perspective, in your point of view, okay, we can measure it quite differently here. So in a simple way, we're writing the relative velocity as this, the velocity of the car relative to the ground. That means that the car's velocity that measured by the person on the ground who's stationary. That is, as you can see, like we're just seeing the car's moving 10 meters per second east. That is the actual speed of the car, the relative velocity of the car as well. But what about this? What about velocity of the person on the ground relative to the car, or simply V, G, and C like this. Again, I want you to think about the situation. You are the one that now inside the car, driving the car. See, I'm moving, and I'm looking you. So I would really want you to have a test study by yourself. Like when you're walking, you're like moving forward, but I'm looking at you, Matthew. It feels like you're moving backwards, but you're moving backwards. I feel like oh, I'm not the one actually moving forward if I'm moving constant speed. I'm saying that you're moving backwards in my perspective. Does it make sense? Kind of makes sense? Okay. This is something that you really test with your views and bodies and like in just a situation. Put yourself in the situation that, think about it. You have to be aware of that. Oh, I'm moving forward, but I'm looking at you. It feels like you're moving backwards. Okay, that is what I'm talking about by relative velocity. It's not actual velocity. You're not moving. I know that your guys not moving, but in my perspective, because I'm moving forward, I seem like your guys moving backwards. That means that velocity of the person on the ground relative or the measured by a person in a car. As I said, I'm moving forward, so it feels like you're moving the same speed as me, but it's just a different direction. That is 10 meters per second to the west. Okay, now this is kind of confusing because every single time we can imagine it, it's hard to imagine this. So this is the reason why we're bringing up some kind of formulas to understand the situations. When we say V something A to the B, I hope you remember that from the previous lesson. It means that velocity to A relative to the B. This is found by velocity of the A minus velocity of the B. Okay, so in case here, I can also just write it as velocity of the A that's measured by the person on the ground minus velocity of the B measured by the person on the ground like this. Again, taking the negative value of the velocity as we are dealing with the vectors, I'm talking about their different direction. It could be the magnitude if they're the same line, but it also could be like in some different directions too. So let's go for the example here. For this example, VC on G can be then rewritten as velocity of the car minus velocity of the ground. Does it make sense? Okay, what was the velocity? So this means velocity of the car that measured by the person on the ground minus the velocity of the ground person like this. So the actual velocity of the car that measured by person on the ground was given as 10 meters per second to the east. That minus the person on the ground was stationary as a given. It means that 0. This is why you get the 10 meters per second to the east straight away. Same reason, V, G, and C. That means again, this a velocity of person on the ground, the relative to or measured by the person in a car. This can be written as V, G minus V, C here like that. Okay, which is what? V, G, G, that's a person on the ground measured by the person on the ground again, V, C, G. This is the same as 0 minus 10 meters per second to the east. Then you'd get 10 meters per second to the west. So this is a method, that mathematical, like a formula method that we can figure out the relative velocity. It's pretty simple when you're just having a 1 or 2, but the problem starts from when we have a 2 dimensions. Saying we have a car. Now let's have a look at the car there. What if the car is moving and the blue car and the purple car is moving like this? Okay. Now, if the 2 cars moving in the same line, same lane, and one car is moving in 15 meters per second to the east. Say this is a car A. Let's make it car A and car B. Okay, and we also have a person on the ground that's seeing that 2 cars together simultaneously. Okay, so let's have a think about velocity of the car A that's measured by person on the ground. Matthew, would it be the velocity of the car A that's measured by the person on the ground? It would be 10 meters per second. What direction? East. Christine, what about velocity of the car B that's measured by a person on the ground? East. There we go, because he sees that as the actual speed of the car. But what if I ask you, hey, what's the velocity of the car A relative to the person in the car B? Okay, yes, we can just straight and use that formula in here, but I really want you to think about the situation here. Person in the car A is moving in 10 meters per second. So what he sees is, I'm driving, I see the car's moving faster than me. But will the car move at 15 meters per second in my perspective, while I'm moving forward? It'll be something that's not as much as a 15 meters per second, because you only see that difference between my speed to their speed. Okay? This is something that you really need to think about it, like in the real-day examples too. The trains, for example, when the 2 trains goes together, when another train started overtaking another one, you only see that difference of the speed between 2. You're not really seeing that the actual speed of the train or the car in this case. After you understand the situation, after you can imagine the situation, then you can put it up into your formula. The VA is V equals to VAG minus VBG here like this. Okay, good up to here. Now, what we have for the VAG previously, that was given as 10 meters per second to the east. Minus, what's a BVG? We found that too, 15 meters per second to the east here like this. Question is, what is the negative of the vector? It simply means we change the direction. Okay, or we can use a sign convention that 10 meters per second to the east in sign convention is known as plus 15. That we agree, kind of made agreement that easterly direction is a positive direction. This would also be a plus 10. This ought to be the plus 15 here like that. And mathematically, just put the negative there. Then what you get is minus 5 meters per second. Considering the negative direction of the east, this simply means 5 meters per second to the west. Does it make sense? Okay. This is how you need to deal with the vectors and the vector diagrams too. We can do the things, the similar things for this one then. What about velocity of the car B, that's measured by a person in the car A? Again, you just do the same thing. V, B, G minus B, A, G here like that. That is 15 meters per second to the east minus 10 meters per second to the east. In the sign convention, it simply means 15 plus 15 minus plus 10 gives you plus 5 meters per second. Taking the positive direction, the plus, that's in the east, that means 5 meters per second to the east, like this. Okay, that's what happened in one dimension, as in like in the one same plane. Now, you probably get a question from your practice and your your holiday homework that we have not only the one dimension, we have a various 2 dimensions to it. Sometimes you get a 3 dimensions if you're unlucky. 2 dimensions, as in like I'm talking about 2 different directions now. So assume that we have a car A again, which is moving in 10 meters per second to the east again. This time, the car B is moving towards the north. Okay? Moving towards the north, say 15 meters per second again. So this is something very tricky and something that's very hard to imagine that, because you gotta imagine that, oh, I'm moving forward, I'm seeing the cars coming north towards to me. So you gotta think about what would be its relative velocity from in here. The rule is always applied the same. So what we have, if I ask you to find, hey, find me velocity of the car A, if that's A and B, relative to the person of the A, you do the same thing. Basically, you do VA minus VB, but I'd rather put the AG and BG here like this. Because what we know is, if we have imaginary person that's standing on the ground, looking at the 2 cars approaching to each other, we will see that VA of the G, car A's velocity measured by the person on the ground, would be 10 meters per second to the east. Okay, same in here. VBG would simply be 15 meters per second to the north. So what we need to do, I'm going to put that in here. So for the VAG, we're given that 10 meters per second to the east, minus that VBG, that's given as 15 meters per second to the north. Now, the problem here is, unlike the first dimension, the one dimension there, we can't deduct the east to the north because they're in the different direction. So what we need to do is, first, we need to convert the unit, to convert the direction according to the negative value. That is 10 meters per second to the east, minus of the north. Remember that it simply means the opposite direction, plus that 15 meters per second to the south. So that goes to the north to change the direction to the south, like this. Once you get it up to this stage here, you need to draw a vector diagram. So 10 meters per second to the east means it's going to this direction like this. That's a 10 meters per second to the east in the vector. 15 meters per second south means going down 15 meters per second, and 10 meters per second. That should be shorter than that here. As east and south making the in the one direction, they're making the perpendicular, they're making the right angle like this. Okay. If you remember that the vector summation that we learned, that head to tail, then tail to head, head to tail. So if the head of the first vector goes to the tail of the second vector, and then tail to head goes, this is the resultant vector then. And from here is simple geometry question then. What you need to do is, the VAV is therefore, you can find the square root of 10 square plus 15 square. You also need to find the angle. The angle would be 10 inverse of the 15 on 10 like this. Slightly more, slightly complicated than like the one dimension, but still, this is like something a pre-assumed knowledge that you probably have as practice from year 8, 9, later year 10, year 7. 15 square and square root of that. Then you would get 18 0.02. So let's leave that to 1 decimal point, meters per second. 15 divided by 10 and 10 squared of that, inverse of that, you'd get 56.3 degrees. So your final answer, therefore, is or you can write it as velocity of car A relative to car B is 18.1 meters per second at, use the direction that's the east, that's the south, from the east, 56.3 degrees to the south. We started from this direction, goes to here. That's a 56.3 degrees then. Okay, that's the deal, things you need to do with the 2D vectors, which is the two-dimension vectors. Again, we had a bit of practice last time too, but we ran out of time, so we couldn't do much practice on this. Give the questions about it in your the homeworks. So today we're going to go through some of the questions related to it. I think we have more questions. Oh, yeah. On your workbook. Oh, I need to give you a print. Okay, page 162 in your module 1 workbook. So write it down over here. VAB is same as VAG minus VBG here like this. Okay. Okay, it's gonna take a minute. So let's have a read the question together, those. Okay, for the 1.12.1.1, car A is traveling south at 60 meters per second. Car B is traveling north at 30 meters per second. Calculate the velocity of car A relative to B. So how the way we can write that is the velocity of the A relative to B, like this, VAB. Okay, it simply means VAG minus BG, okay? And you put it up what you have. You're given that car A is traveling in south at 60 meters per second to the south. That minus the car B is traveling in north and 30 meters per second to the north. Okay, what we have then is negative of the north means the south. So you get 60 meters per second to the south plus that 30 meters per second to the south, again, because negative north means the south. As we're having a one-dimension situation here, we can just add it up. This gives you 90 meters per second to the south straight away. Okay, second question. Hang on, let's just see. Done. Okay. Question B, car B is relative to A. So what we need to do, car B relative to A. It's good to show all the relevant working out. I know it's been running out of space in here. So I try to show all the relevant working out on the board. You can copy that down. VBA means that the velocity of the car B on the ground minus that velocity car A on the ground here like this. That is 30 meters per second to the north minus 60 meters per second to the south. Okay, so negative of south gives you plus the 60 meters per second to the north again. That means you can just add it up. You get the 90 meters per second to the north like this. Okay. Question 2. Car P is moving at 18 meters per second to the east. Car Q is moving 50 meters per second to the west. Car R is stationary. Find the velocity of the first A. P relative to Q. So let's find the P, car P relative to Q. That means car P of the ground minus car PQ on the ground like this. What we're given, P is 18 meters per second to the east, and car Q is moving to the west minus 50 meters per second to the west like this. Change that direction to the east. Therefore, adding up the same direction value, you get 33 meters per second to the east. This is the answer for the A. We can do the same method for the Q relative to P, V Q relative to P. Let's skip some of the things. Then you would get, this means 15 meters per second to the west, okay, minus 18 meters per second to the east. Change that to 15 meters per second to the west, plus 18 meters per second to the west, again, gives you 33 meters per second to the west. So what that means is, depends on the situation. Like, you get the same, you probably get the same magnitude of velocities. You can measure the same magnitude, but you're moving in opposite direction. C, P relative to the R. Now, R is the stationary person on the ground. So velocity of the P relative to R means that velocity of the P on the ground minus velocity of R on the ground. But this person is stationary. Simply, this is same as P was 18 meters per second to the east minus 0. So just leaving you 18 meters per second to the east like this. D, R relative to the P, okay? What about this? R relative to the P. This means velocity of the person on the R on the ground minus velocity of the P on the ground. That is 0 minus 18 meters per second to the east, which means it will change the direction to 18 meters per second to the west. Let's go for the E again to Q relative to the R. So velocity of QR. Say this is simply same as the velocity measure on the ground. So that's simply be 15 meters per second to the west. Lastly, F, velocity of the R measured by person in the car Q. The 0 minus 15 meters per second to the west gives you 15 meters per second to the east. Okay, so if you understood like it's the negative of the direction means simply the change in direction and vector summations, this relative velocity is quite doable questions, to be honest. Okay, I mean, yes, we have some cosine and sine questions coming up, but basically we're using the same methods. Next one, what about this one here? X is traveling at 22 meters per second north. Y is traveling at 12 meters per second north. Z is traveling at 60 meters per second south. Then find the velocity A relative X relative to the Y. Then velocity of the X relative to Y means the velocity of the X minus velocity of the Y. Let's just take that for now. You can use the ground if you like to, but we've got to give it the velocity. X is traveling at 22 meters per second to the north. Then minus that, Y is traveling in 12 meters per second to the north again too. So as they're in the same direction, we can just minus those two directly. That gives you 10 meters per second north straight away. B, Y relative to X, velocity of Y to the X, that is Y minus and X gives you 12 meters per second to the north minus 22 meters per second to the north. This gives you minus 10 meters per second to the north. Now, we do not really take the negative in the direction convention, so we have to show the correct direction. Means negative of the north gives you 10 meters per second to the south. Okay, C. X relative to the Z. So velocity X to the Z. Z is traveling to the south. X is 22 meters per second to the north. Then minus that Z is traveling is 16 meters per second to the south like this. Negative direction again means 22 meters per second to the north plus 16 meters per second to the north like that. Then you to get, adding these two up, you get 38 meters per second to the north. Okay, D is velocity of the Z relative to X. Now, without doing the calculation now, if you understood that, if they're in the same relative motion, same situations, just like I'm moving forward, I'm looking at you, then it seems like you're moving backward, the same magnitude I'm moving forward. Then you would know this Vz to the X would simply be the opposite direction of with the same magnitude. So it'll be 38 meters per second to the south, like this then. You can also do the conductor calculation, but you get the same result. Okay, E, Y relative to Z. That is velocity Y and 12 meters per second to the north minus Z, that is, what's that, Z? 16 meters per second to the north. Sorry, the south, my bad. That gives you 12 meters per second to the north plus 16 meters per second to the north again. That gives you 28 meters per second to the north. And the F, the velocity of Z to the Y, it will be the opposite direction of the previous vector, so 28 meters per second to the south. Okay, doable, not too bad, okay? Now, could you try the last question, the train question then, please? This is something that's very similar to the school exam. You don't get those, but you can get the last question. Okay, this is the situation. I kind of drew the diagram related to for this information given. The car, we have a train A and B. Train A is departing from station X. Train B is departing from station Y. Okay, they both are traveling towards each other. So A is going from X to Y, and B is going from Y to B. Y to X. Okay, the distance or the distance between X and Y is 240, and X to Y is to the easterly direction. Okay, now, question A is asking you to calculate the velocity of the train A relative to the train B. So simply, velocity A relative to B. This is how we need to write it. That means velocity A minus velocity B, or you can just put the ground. That's fine. Velocity A to the A to G. A is moving in 30 kilometers per hour. That's moving to the east, as we can see from the figure out from the diagram there. But train B is moving in 50 kilometers per hour. That's moving to the west. So what that means is negative west, it changed that to plus 50 kilometers per hour to the east like this too. Then we can add it up. That goes to 80 kilometers per hour to the east. This is the relative velocity of the train A relative to the train B, which is true that if you ever seen like in the cars approaching to you, coming towards to you, okay, or if you ever played like kind of rugby, like on the dodgeball, or like some Oztag, if an opponent like is kind of approaching to you, you feel like the person is coming to you really faster than the actual speed. Okay, and then the collision is more massive too. We're going to relate that to like the relative velocity to momentum later on to why the collision between two cars coming towards each other is more severe than car from the back. Okay, that's for A. B. Calculate the velocity of the train B relative to A. That would be, you can use the same method, or what we know is BBA would be simply be the opposite direction of the BAB. It would be negative BAB, like this. That's fine. Then, without doing some complicated calculations, it's not that complicated, but you're showing that calculation, you can get 80 kilometers per hour. That's moving to the west end. You can apply the same method, but you get the same result. Okay, C. Then, how long before they meet? This is the question. How long? Anyone? 3 hours. How did you get the 3 hours? Because we have a distance of the 240 kilometers to east, okay? Okay, relatively, I mean, just thinking about this train in here, this train is moving 30 kilos per hour. So without knowing that B here, if just moving in 30 kilos per hour to go to the station Y, which is 240 kilometers east, you just simply 240 divided by 30. That takes 8 hours. But the question is not asking you how long does it take for A to get to the Y. It's talking about in between. So inside of that, they're approaching to each other. So it'll be 240 divided by relative velocity, any of the A and B, or the speed of that, same as 240 divided by VA in the absolute. Then you to get 3.0 hours in this case. Okay, let's do more questions then. Next page. What about this one? Car A is moving north at 27 meters per second. Car B is moving east at 36 meters per second. Using appropriate vector diagrams to find vector A, velocity A relative to B, and B to the A. So it might be good if you can bring your ruler, projector. Okay. A. So we have car A. Velocity A is given at 27 meters per second to the north. Velocity B is given at 36 meters per second to the east. Again, this is the same as velocity A that measured by person on the ground, imaginary person, and the ground here as well too. So question is asking you then, A, velocity to the A relative to B, simply V, A, and B. We have to rewrite that as velocity A minus velocity B, like this. This gives you 27 meters per second to the north minus 36 meters per second to the east. This, before you put it into vector diagram, put that in to change the direction. This is 27 meters per second to the north plus that 36 meters per second to the north, the west, as the opposite direction to the east is the west. Okay, Once you get that, show that in the vector diagram. Now, when a question asks you to draw a vector diagram, guys, it means that they want you to show in the scales. Use your ruler. So what we have to do, I'm actually using this, the ruler here. I'm taking the 27 times 2, so 50 for my ruler here to north. This is north, 52. This is my vector. In my ruler, this is a 52 centimeters. That's just times 2 of the 27. So in your ruler, you can use your ratio values too. 36 meters per second to the west. Oh, this is going to the west. So I have to draw that. Here, so 52. Okay, make sure the head of your first vector goes to the tail of the second vector. So 72. Goes like this. Okay, this is 36 meters per second to the west. This is 27 meter per second to the north. Okay, then the resultant vector between two is always head to tail, then tail to head. So we just draw a vector from tail of this first vector to the head of the second vector. This is your resultant vector. I call the name that as VAB then. Okay, as you can see, this is a right angle triangle. So to find the VAB, you have to use a Pythagoras, and to find the angle between the two vectors, always start from the in the initial point. Okay, the starting point to measure that where we have to start to draw the vectors from. So VAB, the magnitude is found by Pythagoras, 36 squared plus 27 squared, and square roots of that. That gives you 45. Then angle, which is this angle here, is found by tan inverse of the opposites over adjacent, and tan inverse of that, you'll get 53 degrees. Therefore, VAB is 45 meters per second at, taking the direction north, from the north to 53 degrees to the west. This is same as west from 37 degrees to the north as well too. From there, if that's a 53 degrees, that must be 37 degrees then. Okay. Sometimes we prefer like having this lower the values, so you can just write it as that, but basically they're the same. Or you can also use the true bearing. That's started from all the way goes like that too. There are various methods to show the direction as I discussed before. What about 2? The velocity of the B relative to the A. So let's write it down first, the work I'm working out. Relative velocity of the B to the A means VB minus VA. This means 36 meters per second to the east minus 27 meters per second to the north gives you 36 meters per second east plus 27 meters per second to the south. Okay, we can't really add it up because they're in a different direction, different dimension, so we have to draw a vector diagram too. Now, without drawing the vector diagram, but can you guess what would be the VBA? Yeah, 45. At that is the issue, isn't it? Okay, I want you to think about the negative direction. It means completely opposite direction, isn't it? When something is moving to the west, the opposite direction is simply be the east. Okay, when something has moving to the north, the opposite direction was the south. But what if we have diagonal vector? Would it be it? It would be something in between, goes like that too. That is what we mean by opposite direction in one dimension. So I know we can construct the vector diagram. So it will be something going like this. I'm running out of space. Okay, so the angle would be is either be this angle. Okay, so a little bit of the similar triangle question then. We have these two, or like not even that. This is 37. That means you can get 45 meters per second, which is same magnitude, because we learned that VBA is same as negative VAB, which is the opposite direction. So at the angle of 37 degrees from east towards the south, so that'll be east 37 to the south, or south 53 to the east. Can you see like I switched the direction here too, from north to the south, west to the east. So yes, you can construct a vector diagram, you will get the same answer too, but it's also good to show like some understanding about what I mean by like the negative vectors or negative direction. Okay, all right, what about the next one? Try for the next one, please. You guys, you and me have a different scaling, so let's skip that for now. Let's move on to the next one, 1.13.1.3. Because I have the wrong scaling to yours. Could you try the first question, please? Now, when the question said northeast, it's in between, right in between the north and east, means that'll be north 45 or east 45 to the east. Okay, so that's how, or just simply northeast or northeast. That's how we can write it. Same for the east north. So what is the velocity of the car B relative to the ground? Here we go. This is something that's very tricky. All right, we have to interpret the question very well. The driver in car A who's moving in 20 meters per second. So what we're going to do is I'm going to leave that as this is velocity A on the ground, the actual speed or the speed that measure on the person on the ground, the stationary person on the ground. Now he noticed that car B moves to northeast at 45 meters per second. So it is actually giving you the velocity of the car B relative to the person on the A. Okay, so you have to read the question very carefully. It means that when the person on the car A saw the car B is moving, he saw that car B is moving in 45 meters per second to north, 45 to the east. And the question is asking to find find me the B velocity of the car B relative to the ground, or the actual speed of the car B. Okay, to do so, we have to use this. VBA, as we discussed before, can be found by BBG minus VAG here like this. That's what we learned, okay, in terms of the relative velocity. Now, what we're going to do is, to find the VBG, I can just move that to the other side. That we're making that VBA plus VAG like this. Does it make sense? Okay, then what you get, VBA that we're given, 45 meters per second to the northeast, plus that AG, that's same as 20 meters per second to the east. Again, we can't add these two up just directly because they're in different dimensions. Means that you need to construct a vector diagram again too. So 45 meters per second to the northeast, it'll be something look like this. It won't be in the scales, but let's try my best. That's not a 45. That would be more like a 45. Let's assume that that's a 45 meters per, sorry, northeast. Northeast, yeah. More likely. That's northeast. That's a 45, okay? And the magnitude 45 meters per second again too. And this vector goes to like added up to the 20 meters per second to the east, means that goes like 20 meters per second like this to the east. That is 20 meters per second to the east. Slightly shifted. Here you go. Okay, that's 20 meters per second. Now, the resultant vector between these two is always head to tail, then tail to head. So tail to the head. That is a vector between two. Oh, oopsie, sorry. Okay, now, can you find the vector magnitude and the angle between this one or even that one? Matthew, what do we need to do? This is not a right angle triangle, yeah? If I ask you to find, hey, find me this, what do you need to do? Mm-hmm. Northeast. Or if that confused you, what about we kind of change the direction? What about this one? This is same. I'm making the parallelogram. It's 45. Okay, we're given that this was 45 degrees. Then this angle here must be 135. And it's the same as I'll ask you to find this vector here, because we are dealing with the same parallelogram. Okay, so you're given an angle between 26 and 45 meters per second. We have an angle between them. Can we find the length or some other things too? What is this? Using the cosine rules. Okay, sine and cosine rules too. Okay, yes. Oh, by the way, last year's HSC, we had a question that actually asked you to use the cosine rules. That's like first time in 10 years. Yeah, and otherwise you need to make a big assumption there too. What is a cosine rule again, guys? Cos c squared is equals to c squared is equals to a squared plus b squared minus 2ab cos c. Okay, that's what you need to do. So to find the length of the c, which is that length here, using that, you're to get c squared, which is like a vector vg squared, or just simply vg is equals to 26 squared plus 45 squared minus 2 times 26 times 45, that times cos 135, and square root of that. You get the length of that. So 26 squared plus 45 squared minus 2 times 26 times 45, that times cos 135, and square root of this. Is it 20? Sorry. Oh, I'm confused because of my handwriting. Okay, 20. Thank you. And square root of that. Did you guys get 30, 64? No? Let's try again. 20 squared plus 45 squared minus 2 times. Oh, sorry. It might not be. Cos 135. Square root of that. 61. They rounded up to the whole number, or 60.81. Okay, that's the magnitude of the vector. What about the angle? Which angle do you think we need to find to show that describe this vector? We need to find that. Remember that we need to find the angle that is started from the starting point of the vector, which is it's either be this angle or this angle. Okay, so this is how we can describe these goes into this direction. So we can't really find the angles from this triangle right now, but we can use the sine rules. That sine A over sine A equals to B over sine B. A little bit the other way, capital sine A, the C over sine C. Okay, we can choose any of those. We can use 135, so which means 61 over sine 135 is equals to 45 sine theta. I'm using that angle, finding this angle, theta on 45. Therefore, theta is equals to 61 divided by, or use the exact values. If you have one, that divided by sine 135. Okay, divided by 45. Inverse of that, and sine inverse 31.5 degrees or 31.6 degrees in 3 figs. Okay, to find the exact values here, because we're given north and east, let's use that. Means that we have a situation there. There's vectors going into the 31.6 degrees in this in that direction. So this means that the velocity b to the g is now therefore 61 meters per second at, from the east to the north, east 31 or 32 degrees to the north like this. Okay, yes, you may need to use the sine and cosine rules to find the vectors. You won't get the right angle triangle all the times. A little bit tricky, but I'm just giving you some simple geometric question that you've been practicing from year 9 and 10, I guess. Yeah, you can get that. Could you try for the next one too, please, then? The rainfall question. Try to use the parallelogram to determine the angles if you're not too certain about how to find the length or the magnitude of the vector. Try to imagine about what's going to be happen to a cyclist. So if that rain's coming down vertically, and with the cycle, and at the same time cyclist moving forward, then you'll do facing the rain quite different direction. So that direction of the rain relative to the cyclist will be the direction of the umbrella that cyclist needs to wear. Okay, so using the same terminology, this is actually easier than the previous question, the car question. So the velocity of the rain relative to the cyclist is then, okay, it would be the same as velocity of the rain on the ground minus velocity of the cyclist on the ground, that is 8 meters per second down minus 3 meters per second to forward. This gives you 8 meters per second down plus 3 meters per second backwards. So using the vector diagram again, we have a down of 8 meters per second, and head to tail backwards means going in this direction. The resultant vector would be this, which is in the right angle triangle simply. So 8, and we have a 3. Okay, so find that. Velocity RC is therefore 8 square plus 3 square, and square root of that, you get 8 square plus 3 square, square root of that, you get 8.54 meters per second. Angle would be always started from the starting point of the vector, which is, I'm talking about this one in here. Okay, that is a theta, then theta divided by 10 inverse of the 3 on 8. So 3 divided by 8, 10 inverse of that, you're going to get 20.5 or 21 degrees in. Let's leave that to the 3 specific, 20.5, 20.6, sorry. Therefore, BRC is 8.54 meters per second at 20.6 degrees from north. But you have to talk about the umbrella here. So you need to hold the umbrella. We don't really actually we didn't really need to find out about the direction here. The magnitude. It's more about the angles there, which means in the cyclist's perspective, it seems like the rain is approaching to his face directly. So what we need to do, he needs to wear the umbrella in this angle, same angle, so that he can protect. So it means that he needs to wear the umbrella like this to protect himself from the rain. So the angle of the umbrella, what's spelling umbrella? Umbrella. Yeah, umbrella must be the 20.6 degrees from the vertical. No, sorry, from the horizontal. From that, yeah, it's from the vertical. So it means from the vertical, 20.6. That's how he needs to wear the umbrella to protect himself. I don't think it's possible to wear the umbrella while he's on the cycle. That's more dangerous though. Okay, funny. Okay, let's try one more, and then we're gonna move on to the next question, next type of the relative velocity questions. Lots. So I try to give you some other situations. It's raining is one situation that we can possibly get this type of questions. Cars, obviously, trains. Yeah, I'm going to talk about boats. That's a relative velocity of boat to the river in the river flow. So there are some typical questions that we get. West of the south. West of the south means south, the south of the 30 degrees to the west. west of the south. That appeared. Okay, John skates south at 6 meters per second. A fellow hockey player passes the puck to him. The puck moves at 10 meters per second at 30 degrees west of south. Means from the south, it moved towards the west at 30 degrees. What is the puck's velocity as observed by the John? So what we have given here is John's velocity relative to the ground is given as 6 meters per second to the south. That's given. The puck's velocity relative to the ground, this is the pass for the fellow player, in 10 meters per second to the south, 30 degrees to the west. Okay. Then questions asking you what is the relative velocity of the puck to John. So to find a VPJ, or like the puck's velocity relative to John, simply put it into the formula like this: VPG minus VJG. Now, negative VJG means that, I hope you remember that we simply get this maintain the same magnitude, changing the directions only. So this is the same as plus of the VG to the J. Okay, which means as the VJG, because John's velocity was 6 meters per second to the south, this would be then plus 6 meters per second to the north. Does it make sense? Okay. Now, 10 meters per second to the south, 30 degrees to the west is drawn as the vector diagram like this. Then what we have given, 6 meters per second from that head of the first vector will be something like that. That's a 6 meters per second to the north. That is velocity of the ground to the J. Then resultant vector must be from tail to head, which is this angle here. Again, if that confuses you, you can use the parallelogram because it's basically talking about the same vectors, like this, okay, to figure out the angles between those. 10 meters per second, 30 degrees, and that and that. Yep. So instead of dealing with the triangle on the top, if you're dealing with a triangle at the bottom, you can actually use the cosine rule straight away, which means you don't need to prove that this is a 30 degrees as well, or that is 30 degrees as well too. Okay. Or of course, this is a parallel. There's a parallel, so you can think about, like, SAS, whatever, like alternative angles too. But this is not a math exam. I don't want to see like the proof of that the angles are the same. Just use the parallelogram. It's much better to show that, oh, this is another vector diagram, which makes sense from head to tail, head to tail, tail to head again. Then simply using that to find the length of that, you use C, which is the velocity of the PJ, would it be same as square root of what we given, the 30 and 6, 10 squared plus 6 squared minus 2 times 10 times 6, that times cos 30. Okay, then put that in your calculator. You get 10 squared plus 6 squared minus 2 times 10 times 6 times cos 30, and square root of that. You get 5.67. in 3 sig figs, or 5.7 in 2 sig figs. Okay, or 1 sig fig value will be 6 meters per second. The angle, as I said, we need to find the angle from the beginning of the vector, which is this angle over here. Okay, it's either be this angle or that angle. Okay, or even like in the whole angle of this, the total angles of those. So to find the angles, or like you can find the angle from this side, north to that, which would be better. Okay, let's find this angle, by the way. So it's actually giving you the better terms to find that angle. That would be better angle though. So to find this angle, we probably need to find the angle of the total, which is the same as this angle there. So let's assume this is a theta. Then that angle can be found by, that's a 30 degrees over here, and 6 and that. So sine 30 on the 5.67 must be same as sine theta on the 10. Therefore, the theta, which is, I'm looking for the obtuse angle there, so 10 times sine 30 divided by 5.67, you get, and sine inverse of that, you get 61.86 degrees. Now, what you have to remember is this is not the real angle, like this is from south to somewhere. So assume that we have a 90. Hang on, this is not. Let's draw it again. The 30 and goes there, and that angle, 30 to that. You can use the various methods. Sorry, let's find this angle. My bad. Okay, rather than finding that this angle over here, it'll be better to use this. So sine theta is now be this angle there, divided by, given the 6, then theta is equals to 6 times sine 30 divided by 5.67, and sine inverse of that, you get 31.9, approximately 32 degrees there. Okay, now what we have to concern is this is from there, this is 32 degrees. So you can either use, this is 32. So we have to use that. From that, we have to add up this angle at the bottom. So I redraw that. We have a 30. Okay. We have a 30. We have a 32 degrees over here. The rest of this angle must be then 90 minus, adding these two, 62, giving you 28 degrees. So that angle total, therefore, is 28 plus 32 gives you 60 degrees there. So therefore, your angle is now 60. So velocity Pj must be 5.7 meter per second at, from the direction here, the west and south, we get the west of the 60 degrees to, sorry, east 60 degrees towards to the north. Okay. Feels like I've been dealing with some geometry questions, but yeah. So this is, again, something about 2D vectors. Well, we're going to have a short break, and after that, we're going to go through some of the different type of questions again, too. Okay, let's have about a 5 minutes break. From the relative velocity questions, a boat in like a running river is one of the famous questions they can get as well too. Another one is plane, where they get some wind affected. So let's have a read that, go through this question together now. So two identical boats can move at 8 meters per second in still water. One heads straight out from the bank of the river, which follows at 4 meters per second. The other heads straight out from the bank of the river, which follows at 6 meters per second. Both rivers are 120 meters wide. So I want you to think about, imagine about situations in your perspective. Assume that you're on the person on the boat here like this. When you're seeing that, you'll think like you're moving forward. Okay, so you kind of set the direction towards the forward, saying like to the easterly directions. But because the river is flowing, like, and it kind of keep pushing you, the resultant direction would be somewhat different to what you aim to. Does it make sense? You get keep pushed by the water flow. So this is something that you have to understand in here. A, what is the velocity of boat X relative to the water? So you have to understand what we mean by relative to the water there, and relative to the ground here, starting on the bank. Okay, boat X is relatively moving to the water side A. So the velocity of the boat X to the water, we have to interpret that as this is actually your set direction inside of the boat, your intention. Okay, so the boat X kind of intention or like a target was velocity was given as X was moving in 8 meters per second was the and forward. Which means I want you to think about your situation here. You're in the boat, you're looking down the water. Okay, that means you're probably seeing like you're going forward all the times, but that forward doesn't mean like you're going into this in the right direction. All right, which flows river. Okay, the starting point of the bank. So it's the starting point of the bank. Okay, what is the velocity x, y relative to this? Okay, x across the river. Okay, let's do that here. B, what is the velocity of the boat y relative to the water? Same here. So we give 8 meters per second to the forward again. C, what is the velocity of boat x relative to its starting point of the bank? So this is what I mean here. Assume that we have a person on the starting point. Looking that boat is moving and they're going across the river. Yes, person on the boat would see that, oh, I'm moving forward in 8 meters per second. This is how like what they see in their perspective. But on the person on the bank, a person on the ground would see that the boat is actually moving diagonally because it constantly get pushed by the river flow. So what that means is this: the velocity of the boat x relative to the ground would be something like the diagonal vectors like this. Does it make sense? Okay, this can be found by this. Velocity x of the ground can also be found in this method. Velocity of the x on the water, okay, minus velocity of the water to the ground like this. This is another method that we can find the relative velocity. That you can just assume that when we minus in two vectors, we are deducting from the last w to the first w. So this gives you velocity xw was 8 meters per second forward. Okay, then minus that, the 4 meters per second of water's velocity relative to that. So it would be 4 meters per second to down, resulting in 8 meters per second forward plus 4 meters per second to down like this. Sorry, they're up. Oh, sorry, other way around. It means that ground to the water, meters per second, so to the that'd be up and down. So as a result of that, we get 8 meters per second forward, then added up to the 4 meters per second down. The resultant vector is this. This is the actually person on the bank will see that the boat's movement. And what we do from here, we get the 8 squared plus 4 squared. And square root of that gives you 8.9 meters per second. The boat is now moving 8.9 meters per second. With the angle here, would it be 10 inverse of the 4 on 8, which is half, 10 half. You get 27 degrees there, which means, therefore, the velocity of the boat relative to the person on the ground or the bank is, I should say x, is 8.9 meters per second at 27 degrees from that direction of the movement. So that is 27 down there from the horizontal. Okay, ignoring outer space. Okay, we can do the same method for the question D. The velocity of the boat y relative to the person on the ground, like that. Okay, this can be found by velocity of the person, the y, on the g, sorry, the water, means that the person on the boat y would see that he's moving in 8 meters per second, but it's in his perspective. Okay, or seeing that water perspective to that relative to water. Okay, the minus velocity of the ground to the water in here, like that. You get the 8 meters per second forward minus that the 6 meters per second. Now, when you see the water as like moving down, seeing the ground, person on the ground, it's got to move in the opposite direction. So rather than saying the up, it's actually moving in. Sorry, down is moving up. Gives you 8 meters per second forward plus that 6 meters per second, so down like this. Then we get the vector diagram of 8 meters per second forward and 6 meters per second down. This gives you the 8 and 6, so 8 squared plus 6 squared, square root of that. You get 10 meters per second, and you also get the angle in here, the 10 inverse of the 6 on 8. You get 37 degrees there. Therefore, the actual velocity, like the boat is moving on the perspective of the person on the ground, would be 10 meters per second at 37 degrees from the horizontal. Okay, then how long will it take the boat X to cross the river? For E, the boat X is actually moving in this velocity, 8.9 meters per second there. Okay, I hope you remember, like, we have a river on the Y, the river is 120. Okay, and this person is moving downwards, into this direction. Okay, so he's actually moving further, further than 120 meters because he's moving diagonally in the speed of the 8.9 meters per second. And this person is moving in the 10 meters per second like this. Okay, so the way we can find that the distance, the extra distance is, we got to think about the right angle triangle over here, okay, with the angle of the 27 degrees given over here. Then you can find, as taking the 120, you can find the length of this extra distance that the boat moved. So to do so, it'll run out of space. The actual, so question E, the actual distance, the travel by the boat is using the trigonometry. So we have a triangle look like this, the 27 degrees, 120 meters. That is the distance that we are looking for the hypotenuse. So this is as cos 27 is equals to 120 on the actual distance x. X is 120 divided by cos 27. Gives you 120 divided by cos 27. You're going to get 134.7 meter is the actual distance that the boat is moving in the speed of the 8.9 meters per second. To find the time, as you remember that distance is equals to velocity times the t, then t is equals to d over v, that is 134.7 meter divided by 8.9, the speed. Then you get 15.1 meters, the seconds to travel that distance. Okay, so you have to understand, the boat is now no longer moving 120 meters because it's not really directly across the river. It's going diagonally, so moving further than 120 meters. Same for the question F, that we can use the same method that we have an angle. Does anyone have the angle we have from question D? 37, thank you. I should write it down. Same. So we have a right angle triangle that's moving 37 degrees then and 120 meters. So what we have, the extra distance, x would it be the 120 divided by cos 37. That you'd get 150 a meter to travel now. So that's therefore the time you take is 150 divided by the velocity, which is 10, gives you 15 seconds to travel that distance, or 15 seconds to cross the river. Then question G. How far downstream relative to the starting point will boat X reach to the other bank? As you can see, boat is now moving across the river directly, just forward. It's going downwards and reaching to over here. Okay, so how far? Boat is now landed on the other side of the bank, and with the angle of 27 degrees given over here. Then we can also use, what's the question is, FG, the right angle triangle. That is, this is giving you that 27 degrees. The distance from the river right is 120 meters. This is where the boat is now. Makes sense, okay? So if that's the starting point of the boat, now ended up it landed onto this point over here, you just need to find this one from the starting point. That is, let's say taking this as a y. Y would it be, using the trigonometry again, to sine 27 from this right angle triangle is tan 27, I should say. Tan 27 is y 120, therefore the length of y is 120 times tan 27. So 120 times 10, tan 27, you're to get 61 meter. That means the boat will land at the 61 meter down of the from the starting point. H is the kind of similar questions too. So we just use the right angle triangle. That is, instead of 27, now we have a 37 degrees. So tan 37 with 120 equals to y on 120. Therefore, y is equals to 120 times tan 37. Gives you 90 meters down. Yes, we feel like we're dealing with some geometric questions quite a lot, but this is quite common in the vectors that we have to deal with angles and length of that, therefore find the result of vectors. That's H. I explain why the speed of the river does not affect the time to cross. So what we have seen is the time is almost the same. Can you see that? Time is almost the same. For the even you get pushed by the river, because it was moving at 8 meters per second. Let's think about like what if there is no river flow? What if you're moving in the still water? Then the time you take is t is equals to basically d on v. The boat is moving at 8 meters per second forward, and the crossing the river 120. That divided by 8. 120 divided by 8. Do you get 15? You get 15 seconds as well too. Now what you see there is, even though the boat is pushed by the river, okay, it's traveling in almost like the same speed, the same time. It's reached to the at the ends in the same time too. Okay, the question is asking you that why is that? Why the speed of the river does not affect the time to cross? Okay, to understand the point in here, you have to understand about the diagonal vector. When we have a diagonal vector like this, okay, a diagonal vector, it must have a horizontal and vertical components to produce the diagonal vector. Okay, what I mean is this is produced by this horizontal vector plus this vertical vector. Does it make sense? Okay, same for even though we have a great stiff vector like this, we have horizontal vector and the vertical vector combinations. Now, what you're given in the situation here is the boat for both situation here, crossing the 120 meter wide river, is moving at 8 meters per second for both of them. So I drew the two vectors representing that. One is 8 meters per second, 8 meters per second of boat. Another one is river flow. It wasn't like actually 4 meters per second. The wrong diagram, but exaggerated. 6 meters per second like this. Okay, so even though we have a different diagonal vector due to the vertical vector differences given here, okay, as the horizontal vectors are the same. Okay, and considering about the distance they're moving, this movement to reach the other directions, and the river wide is remained as 120 meter. Okay, the time will take, the time taken to cross will always be 120 divided by 8. That is 15 meters per second in this case. We're probably going to talk about more about horizontal and vertical vectors in the projectile motions in year 12, but that's what I mean here. We keep the same horizontal vector of the 8 meters per second, and if you consider about like a vector displacement from here to there, it also has the same displacement of the 120 meter in the horizontal vectors. There's a reason why the time doesn't really get changed, but what it changed the landing point. Okay, it changed that about distance, the actual distance they traveled. This is kind of confusing point. This is why I picked the boat questions as one of the hardest you can get in the relative velocity. The wording is quite difficult too, so this is very important that you understand or imagine about you're the one inside the in the boat on the boat, or you're the one that is looking up the boat and moving across the river. Okay. Explain the speed of the river does not affect. Okay, we did that. J, at what angle to the bank does the boat X need to hit in order to reach the far exactly opposite in the starting point? Okay, could you try the question J, please? I'll write it down, 27, Y37. So you have to understand the situation given in here. When the boat, the captain of the boat is moving forward, okay, because the river flow, it get pushed downwards and forming the resultant vector, they're going diagonally like this. But if the captain wants to land the same point where they started from, same level, okay, you may need to think about it in this here. They can't go forward straight away because they knew that they will reach to the somehow the down from the landing to the starting point. In other words, if they goes to this diagonal direction, as they gradually get pushed by the river flow, it will make it into the reaching to the point X as well too. The question is asking you, hey, what would be the optimal, the good angle to go to the X, the same level as the starting point? We found that this was going here. So I'm going to draw a parallelogram then. If this reaches to this direction due to that river flow, and we want to get there, then if the boat is heading towards to the same angle, with the same angle there, because it gets pushed by the river, it will end up to comes to the same level as that too, in terms of the parallelogram. So the X, for X, question was that the J, moves into the 27 degrees upwards, or the 27 degrees above the horizontal. Okay, Y would it be 37 degrees above the horizontal then. Therefore, at the end, ultimately, they can reach, and they landed at the same level from their starting point. Okay. K, how long will it take the boat X to cross the river if it follows the direction you calculated in J? So let's have a think about it here. They move upwards and they move down. They kind of gradually push it down too. But as there's the same reason here, as they did not change up the horizontal vector, they're still crossing the same amount of the horizontal distance, which is 120 meters, okay, and still moving 8 meters per second in this case. So let's have a think about it here. We have a vector now is moving in 8 meters per second at the angle for X, at the angle of 27 degrees there. As you know, you get pushed by the river flow, which is 4 meters per second like this. And the resulting then ended up point over there. And we have formed a new right angle triangle that this second triangle is 120 meter. That's 27 degrees given here like this. Then the extra distance that, it'll be actually something look like this. Cross that with, and it get pushed by the river and goes like this. So we have a 27. What would that be? About a 27 goes up, pushed by that, and gradually coming down. Yeah, this is the right angle that we need. Okay, so 120, and this time here, this is moving in 8 meters per second. So you have to realize the difference between the previous question to this. Previously, we had a situation where right angle triangle is formed by 8 meters per second horizontal and vertical 4 meters per second, therefore move this much of distance. Yep. Okay. Now I want you to think about here. The boat was heading towards the diagonally, going this direction, get pushed by, gradually pushed by the river, coming back to the same point of the starting point like this. Okay. Then, which means that the extra distance to travel by will be quite different to this 8 meters per second going in this, and 4 meters per second. That would be 120 meter. And the extra distance is trouble would be, it'd be actually doing similar or the same. Yep, sorry, it still be 12 seconds because we have it kept in the same time. So just write it down 12 seconds as they're moving the same horizontal distance in this case. Okay, all right, let's try a similar questions about the boat on page 166, please. Skip about the other questions there. Question 1.14.12, this one. Could you try the answer the A to G, please? Okay, let's have a look at that question together now. We have a boat can travel at 2.5 meters per second in still water. River is 45-meter wide and flows at 1.25 meters per second. The boat sets out to cross the river and heads straight across the river, rowing at 90 degrees to the bank. If it holds this course, first, find its velocity relative to the water. So it's given that it can travel 2.5 meters per second in the water, so it doesn't really matter if the river is flowing or not. The sailor or the captain on the boat will still see like moving in 2.5 meters per second in his perspective. So the velocity of the boat relative to the water, in this case, would be, say, 2.5 meters per second. Okay, We're not too sure about the direction. We just probably need to say the forward in this case. Question B, its velocity relative to the starting point is something like here. So if we have a person on the ground or the starting point, obviously as the boats get pushed by the river flow, which is moving in 1.25 meters per second, you would see that the boat is actually moving into this direction. It's actually getting accelerated as well too. It's getting faster by the push of the river. So to find that, we need to use the Pythagoras, that is 1.25 square plus 2.5 square root of that. This will gives you the 2.8 meters per second. This is actual like speed of the boat relative to the person on the ground in the starting point. Then C, in what direction it needs to head in order to reach the opposite side, directly opposite to the starting point, which means if you want to go to this point over here, you need to head up your boat to this direction. So as you're going this diagonal direction, you constantly get pushed by the river. You are actually moving forward. This is something that we have to understand. Like, I try to go like in the diagonally, but as I get pushed by the river, I'm actually moving forward. Does it make sense? Okay, so to find the angle, we have to find the angle between these in this triangle here, the 2 point. So the boat is moving in 2.5 still. There's something. Okay, I want you to figure out the difference between this triangle to this triangle there. Okay, this is when the boat is moving forward, just moving directly forward as in 90 degrees from the ground. The boat is now sailing in the certain angles. Okay, so what we have to spot out the difference between these two is in this right angle triangle, it's not the hypotenuse. It's one of these lines. One of the vectors are the horizontal vector is 2.5. But as you're sailing now in angle of the theta, your hypotenuse is 2.5. No longer be like one of the lines over here. Does it make sense? Okay. Still having that 1.25 meters per second from the river flow, then you have to find the angle by tan inverse of the 1.25. Sorry, on 2.5, which gives you 30 degrees. Does it make sense? Okay, so that's I probably made a mistake from the previous question. That this is actually how you need to figure out the angles that you need to move to, so that you can reach to the same point as before. That was for D. E, in velocity, in what's velocity relative to water. So even though you're moving diagonally inside the river there, in your perspective in the boat, you're still moving in 2.5 meters per second. I'm talking about person on the boat that's moving towards that. So you're still moving in 2.5 meters per second. Then its actual velocity. Now I have a look at it here. The person on the ground and looking up the person on the boat again. Yes, the person inside of the boat would say like, oh, I'm moving diagonally in 2.5 meters per second. But in the same time, it constantly get pushed by the river flow. So a person on the ground in the banking of the starting point would actually see that boat is moving straight this time, unlike the previous situation there. Does it make sense? Can you spot the difference between two situations here? One is the boat is trying to go forward, but because of the river flow, it gets moved diagonally down. Second situation here is to reach the same level, the boat is now going diagonally up, get constantly pushed by the river, so it's actually moving forward. Yep. So we can find that using the Pythagoras that the x, let's say the x would it be square root of the 2.5 square minus 1.25 square. Then you to get that 2.17 meter per second is the actual speed of the boat that measured by the person on the ground. You okay, Matthew? Does it make sense? Yep. So it's actually getting slower than before because Yeah, obviously, you're moving in 2.5, but as you get pushed by the river, you're getting decrease in some of the speed. G, how long it takes to cross the river. So you're now moving in 2.1 meters per second forward. The river is 45 meter. Therefore, to find the time taken, that is distance divided by the velocity, which is 45 divided by 2.17. The time it takes to cross the river in the same level would be 20.8 seconds then. Okay, so you have to understand the two situations there where you are just going straight, get pushed by the river, therefore reaching to some of the points, or you are trying to get into the same point as your starting point so that you start sailing up or diagonally and get kind of pushed by the river, therefore you're moving forward ultimately. Okay, all right, try for the next question. This is something very similar, and we're going to move on to some other different type of questions, which is a plane type. Yes. Yeah. Try that. Motorboat. Okay, remember these two triangles, and there's some terminology given over here. Okay, I'm showing you that in any other situation, the boat questions, you can figure out the velocity of the boat relative to the ground can be found by velocity to the boat to the water plus the velocity to the water to the ground, like this. Okay, so that is not really given on your formula sheet, but you can use that as some sort of formula. And make sure you understand the two different types of the triangles. One is when the boat is trying to go forward, get pushed by the river to end it up to reaching the down at the starting point. Then the boat decides to go to diagonally up, okay, get pushed by the river and reaching to the same level. So this is actually extra speed of the boat measured by the person on the ground then. Yeah, okay. It may not be always be like a right angle triangle though. It may be like sometimes you need to use cosine and sine rules again too. Depends on the situation. I think like question 1.3 is not the case, but next one is pretty much sine rules. But 1.3, a motorboat traveling at 3 meters per second and east encounters a current in the river traveling at 1.75 meters per second to south. Christine, I just kind of summarized the terminology here, so you could just I can take a photo if you want to, or you can just copy it down. It's up to you. All right, we have a boat now moving into the east. That's 3 meters per second to the east, like this. And get the river flow. That is, river is moving in 1.75, so it's actually smaller vector than expected. To the south, like this, in the river. Okay, what is the resultant vector? So what we have is we have a 3 meters per second to the east and 1.75 meters per second to the south. Remember that I can use the same terminology here, that this is velocity of the boat relative to the water. Okay, in other words, you're on the water, above the water, so seeing the boat is moving. You're seeing that the boat is moving in 3 meters per second. This is the same as the relative velocity of the water relative to person on the ground. Assume that we have a person on the starting point on the ground. Okay, then you can find this vector here, which is the velocity of the boat relative to the ground, is bounded by velocity of the boat relative to water plus velocity of water to the ground, like this. Simply just find use the trigonometry, or like a Pythagoras. Then you get this is the same as 3 squared plus 1.75 square. You get the magnitude of the 3.47 meter per second. Now, in terms of direction, as you're given the direction of south and east, you must use those directions given. I'm talking about this angle here. The theta can be found by tan inverse of the 1.75 divided by 3. That you to get the 26.8 degrees given here, like this. Means that two methods. I'm gonna write the two methods. So velocity is therefore of the boat relative to ground is 3.47 meters per second at 26.8 degrees downstream. Is the one method that we can write in the direction. Second is we can use the bearing. True bearing would be from the 9 plus then 90, so all 116.8 degrees bearing. Again, it's good to use some bearings to determine the direction, because you never get it wrong with the true bearings if you're not too sure about how to write the directions correctly. That's A. B. If the width of the river is 90 meters, how much time does it take the boat to travel shore to the shore? So there are two methods to find the answer. One is we find the actual distance that boats travel, okay, using another trigonometry, and just divided by that the velocity you found in here. So let's do the method one. Is find the distance is using the trigonometry that is a 90 meter wide. The angle is given as 26.8 degrees there, here, like this. This is the actual distance that traveled by the boat. To do so, using the trigonometry, cos 26.8, if you're not too sure how to use it, just write it in this method, over x. Then x is 90 divided by cos 26.8, which gives you that. 90 divided by cos 26.8, you'd get 100.83 meter. This is the actual distance that traveled by the boat. So therefore, the time take is distance divided by velocity. So 100.83 divided by the speed of the boat in the relative in the actual speed, 3.47. You'd get 29.5, which is roughly 30 seconds if you take the exact value. This is the first method. The second method is you take the horizontal distance only, okay, and take the horizontal speed of the boat. From the vector diagram here, the horizontal speed is at 3 meters per second. Okay, which means that regardless how long it's like it moves diagonally or not to, in every second the boat is moving in 3 meters per second forward horizontally. At the same time, to move down at a certain velocity, 1.75. So what we take is we just take the horizontal velocity and horizontal distance, which is the river wide. Then t is equals to d over v, simply 90 divided by 3. You get the same result, 30 seconds to across the river. Okay, you can either use first or second method, but you probably get the same answer. You maybe do a change in the method. The way you choose the method is going to kind of vary sometimes, but I don't mind to say both. C. What distance downstream does the boat reach the opposite shore if it initially heads straight across the river? Which means the question is asking you, hey, we went across the river, but we ended up going to here. So find this distance. Okay, that's for question C. Then y from this right angle triangle can be found by, okay, the tangent is using that 10, 26.8 is the same as y on 90. Therefore, y, the actual distance is 90 times 10, 26.8. And you get 45.5 meter downstream. B, if the river current had been 2.5 meters per second, how long would it be has been taken to cross the river? Again, it doesn't really matter how fast the river is moving because you are still traveling in 3 meters per second horizontally with the same width of the 30 seconds. So it means that 30 seconds. Again, the vertical, which is river speed, does not really affect the speed of the horizontal speed at all too. So in this case, yes, the speed of the time taken to across the river will be the same as 30 seconds. Exception is if this is not right angle triangle. If this is not right angle triangle, what I mean is if you're going into this direction, but the river is flowing in this direction, you can't use that assumption. Okay, you have to use you have to follow the first method to find the time takes. Okay, this is only apply for like when you're going across the end, you know that they're making a right angle triangle like this. E. How far downstream would we have reached the other side if the current flowed at 2.5 meters per second? I just give you the answers for this one. If you go that, you get reaching 75 meters down, which is further down. The lastly, F, what would have been the velocity of the boat relative to the water? In this case, yeah, you can just find that answer there, 3.91 meters per second at 39.8 degrees downstream. Kind of same working out, so yeah, let's use the time to do some other questions related to the relative velocity. Okay, this is the boat question, kind of typical question you can get to. For next week, try the question the next page. This is something a little bit twisted in the boat. Okay, give it a go. We're going to go through the answers together next week for this boat. Okay, now let's move on to some plane questions then. Not the cars. Cars are pretty straightforward. Page 170 on your workbook, please. The plane in the crosswinds. This is something that somewhat similar to the boat question, that as you realize that when the boat is moving forward, as it gets pushed by the river, it moves diagonally. So similar things happen in the plane. Let's have a look at the question here. A plane can travel at speed of the 80 meters per second north with respect to the ground. Determine the resultant velocity of the plane if it encounters as a 10 meters per second headwind. Okay, let's have a think about what I mean by headwind and tailwind. I remember in one of the schools, like Sydney boys, they actually get the side wind as well too in HSC trials, which was quite unexpected. Assume that we have a plane Okay, going into this direction. Let's say this is moving to north. Okay, and that's moving in 80 meter per second to north in this direction. Now, meaning of the head wind. Sorry. Okay. Okay. Meaning of the headwind is the wind is blowing from the head to the head. So this is what I mean by head wind. Okay. The tailwind is the opposite. It's actually blowing towards the tail. So it's given that for question A. Headwind is given at 10 meters per second. So it's going kind of opposite to it. So I want you to imagine about you're on the plane, but you get the headwind of 10 meters per second. You got some sort of the resistance there. Then obviously you're not gaining the velocity or the speed, you're losing it. And simply, we can find the speed of the plane again using this. You can use various methods, or you make the diagram too. The velocity of the plane is now be velocity of plane to the ground minus velocity, the actual speed, the wind to the ground like this. I'll add it up to. So that's giving you 80 meters per second. Should be minus. Had wind going down. Oh, should be plus. 80 meters per second north, plus that to the 10 meters per second to opposite direction south. Giving you that 70 meters per second to north, as we know that 10 meters per second south is same as 10 meters per second to the minus 10 meters per second to the north, like this. Or simply thinking about, yes, you get some resistance, you're losing that much of the velocity too. Okay, you get some crosswind. Okay, yeah, it's hard to get through that. Similar reason, the B would be simply be to get tailwind, it's the same as as the headwind speed, 10 meters per second. This will give you that 90 meters per second to north then. Okay, now what about this case? We have 10 meter per second crosswind from west. Okay, if we take this is north, okay, that means this coming out of the page would be your east, coming into the page would be the west. So it means if we have a north going to this direction, that would be south, that would be west, that would be east. Does it make sense? Okay, can you picture that? Now, question's giving you from the west. From the west means that the wind is blowing from the west to the east like this. So it's kind of pushing that plane towards that too. So what we have to do is we have to construct the vector diagram. We have a plane. It's going into this north. Okay, you get pushed by the wind from the east, west to the east, which is this. Okay, or we can think about north pushed by the west, east, west to east like this, which is the same kind of similar triangle in this case. Then resultant vector is this way. Then we have plane's velocity is 80 meters per second. It's actually smaller than we thought, 10 meters per second there. But that is a resultant vector. To find that, okay, north and east that, the magnitude would be 80 square plus 10 square root of that in the right angle triangle as you were given. That simply gives you the 80.6 meters per second. By the way, the meters per second doesn't make sense. That's too fast. That should be kilometers per hour. Doesn't matter, okay? And the bearing, okay, let's think about it here. We're taking into consider the north and they get pushed by the west. This is a resultant vector. And we're looking for this angle given over here. Then angle would be simply 10 inverse of that 80. And we have a 10 and 10 on 80, which gives you that 7.1 degrees. Therefore, your final answer is it's moving in 80.6 80.6 meters per second at. Let's talk about some use of various methods to use describe the direction. It's either be north 7.1 degrees to the east, or the bearing of the or 7.1 degrees. The true bearing of that. Does it make sense? Okay, it's not that complicated once you understand the relative velocity and the vector sum. D, 40 meters per second wind coming from the behind the plane on the bearing of 120 degrees. Okay, I would like to give it a go at this one, please. D. And once you finish the D, you can try for E as well too. These two will be the last questions that we're going to do today. You really need to understand what I mean by behind the plane on a bearing of 120 degrees there. This means from this north, which is the direction of the plane, 120s from that, the bearing side. So we're moving this for 120 degrees, or you get pushed as you're coming this way, the 120. Okay, so you can think about this produced, let me use the different color. That's what I mean by the 40 meters per second, which we can construct a parallelogram again. Let's see. That's a 40 meters per second like this. And you can think about the resultant vector would be somewhere here. Or same as this one. Okay, simply you just need to find that, and what we have to do, we are given 120 from this triangle. Okay, can you see that? This triangle there, we have an angle of 120, 80 and 40 given here. Then using the cosine rule again, so you can find the magnitude of this vector. So using cosine rule, let's give it over here again too. The velocity of the plane relative to the ground right now would be then actual plane a squared 8 squared plus 40 squared minus square root of that 280 times 40 times sine 120. That gives you that 105.8 meters per second. Okay, now angle. We have to find the angle within here, this angle, or this angle here. That is the angle we are designed to get because it's moving from the north side of that too. So to find this angle, which is equivalent to this angle there, we can use a sine rule that angle sine theta over 40 is equivalent to sine 105.8 divided by given the length, which is, what was that length? Sorry, not the length, 120. Sine 120 on 105.8. Therefore, the angle must be then at 19.1 degrees given here like this. Therefore, your final answer is then the velocity is 105.8 meters per second at the bearing of going all the way through. It's got to be 100 bearing of 340.9 degrees, or using the direction north 19.1 degrees to the west. Okay, what about question E? 120 meters per second wind towards the plane on a bearing of 240. So you have to differentiate the difference like between these two. The question D is saying coming from behind. Okay, this is why coming from behind we show that vector. What if we have towards the plane? Towards the plane. Towards the plane. Towards the plane. So let's draw that first vector that we have a plane that's going on up north, I should say up north, that's 80 meters per second north. When we say that wind towards the plane, it's actually blowing towards, so it's going towards to that plane, as you can imagine. It should assume that we have a plane that's going in this direction. Okay, so wind is kind of blowing towards to this direction with the bearing of 240. So thinking of a bearing, that 240, the 180 goes, this is the direction of the bearing then. Okay, that's a 240, which means it will push that plane and then the bearing of 240. That means it will move down. It's either be going like this, affecting the. And what was the angle? 120. It's actually longer than what we have. 120. That's 120 meters per second. And the bearing of the 240 given here like this. Does it make sense to all about this one? Okay. Then the angle here would be, we have this angle must be 240 divided minus 90, 180, so it gives you 60 degrees given here like that. Does it make sense to all? The resultant vector between these two must be from tail to head, which is this. Is the resultant vector that we have to find. Again, another like cosine and sine rule exam question that you have to deal with. So we have given two lengths of the 60 degrees given under here. Yeah, I can just give the answer for that. Velocity would be, the resultant vector would be 120 meters per second at it's not 120. I'm sorry, like it's too fast. Question E is actually moving in 69.3 meters per second at, that would be 30 degrees, by the way, north, 30 degrees to the west. That's the final answer. Or the bearing would be adding up that 360 bearing of the 330 degrees. Okay, so we keep using the same rules again and again and again that draw the vector diagrams, but I'm trying to give you some different situations, like different like scenarios that we can have a boat, we can have a car, we can have a train, we can have a plane, but just helps you to realize that, oh, you have to imagine about what if that goes to, and just be careful with the word plane in here. This is kind of confusing, especially the plane, because they have to deal with winds blowing towards to, winds from, winds coming like goes this direction. Okay, and that makes a huge difference in about writing the answers, finding the answers, and calculating the values. So it's something that's very tricky. So for the homework for the next week, I printed out some extra questions on the relative motions, and I posted up in your class 365. So I gave you 2. Okay, so that's your maze. That's handy in homework. Go for the rest of the questions in your plane and the boat. We're going to go through some more questions related to that, and the next week we're going to move on to the module 2, especially the question at the last. They're not that easy. So give it a go. Forces. I haven't touched the force yet. I haven't started about Newton's law yet. So we are revising some Newton's law, which is quite tricky, but it's getting more tricky because we got to think about some scenarios that what if we have pushing of them, pushing of that in terms of net forces. Okay, it's once you understand the vector diagram in here, it's quite interesting, and I introduced a very important concept about net force too, and this is something that requires you to imagine about what if we have a net force of 0. That's for next week, by the way. Okay, or the week after. It depends how much we can go through with this relative velocity. That's it. See you all. Have a good day.